Good. Very briefly, just a few words about AMS Technologies. We are a company headquartered in Munich with 35 years of activity and offices across Europe. We are distributors and solution providers in the fields of optical technologies, thermal management, and power technologies. We have production facilities and capabilities of DPSS Q-switch lasers, optical assemblies, and thermal stabilization equipment. And I'm the regional sales director of AMS Technologies in Spain. I wanted to talk, or I'm going to talk about two technologies that have a good potential given a post-COVID scenario where prevention of new pandemia will play an important role. The first is the use of Germacidal lamps. Now in the picture that you can see on this slide, you can see what is the optimal wavelength range for disinfection, which is in between the 200 and 280 nanometers wavelength range. There are mainly three types of lamps that are emitting on this wavelength range. One is the mercury-based lamps, the other is the excimer lamps, and LED lamps. I'm going to concentrate my presentation on the excimer lamps. The excimer lamps are sources operating over a wide range of wavelengths and in the ultraviolet spectral regions. They are based on rare gases, and depending on the gas used, the lamp will emit at one or another wavelength, quasi-monochromatically. There are few benefits of these lamps compared to the other technologies, and one which is quite important is that the gases used are non-hazardous. So if there is a leakage, there won't be any environmental problem. They are instant on-off, so in less than a second, you can achieve 100% of the output. The excimer is not affected by the changes in the ambient temperature. That means that there is no microbial reduction capability if the ambient temperature changes, and it also has a high energy radiation. As a con, this kind of technology is more expensive than others like the mercury-based lamps. In this slide, I'm showing you lamps which are filled with Crytone chlorine gas. Why this? Because this is emitting mainly at 222 nanometers, as you can see on the picture that is shown on the left side. And why 222 nanometers? Well, the 222 nanometers, there have been many new studies that are showing that this is a special wavelength and unique, which is similar in terms of bacteria killing ability to other wavelengths, but has not the negative side effects of the two other wavelengths like the 254 nanometers. What are the negative side effects? Well, the typical are skin aging, photocataractics, photokeratitis, well, and even skin cancer if you have prolonged exposure to 254 nanometers. So the topic is that the 222 nanometers wavelength is not penetrating enough to the proteins or the cells that are deep in the skin of the human. So it are in their majority absorbed by the dead skin cells that you have on the skin. As I mentioned, there are many studies ongoing. So if you Google in a website or in a searching tool 222 nanometers or 222 nanometers versus 254 nanometers, you will find a lot of papers related to this. The University of Columbia, Kitasato Research Institute, Nature also have published a documentation out of that. So it's as I mentioned, it's a wavelength that we can say that essentially inactivates microbes, but does not harm human skin. Nevertheless, as you can see, the Crytone chlorine lamps still have some energy in wavelengths that could be dangerous. So in order to be totally safe, it's needed to install a bandpass monochromatic filter. And furthermore, also you have to take in consideration that we have a European regulation which was made in 2006. And it's also regulating, which basically is regulating the radiation exposure that the human can have. And of course, it's regulated the 222 nanometers. And since this law was done before all these studies have came, we still, until we don't have this change, cannot use this in order to accomplish with the law in occupied rooms. But we expect that this is going to change soon. So what about if you want to do a disinfection lamp based on excimer lamps? Just put here some information about the variables that you need to consider, like are the ones that are here. Then you will determine the light intensity on a substrate plus the exposure time that is required, which means that you will determine or specify the UVC dose required. Here is an example. You can see in this table, target microorganisms, exposure time that you will require to reduce it at 99.9%, giving an intensity of 5 milliwatts per square centimeter. So in example, influenza will be inactivated at 99.9% in 1.2 seconds with an intensity of 5 milliwatts square centimeters, given a flat surface. So there is a lot of variables to take in consideration, but this is a process that it needs to be defined in order to design properly disinfection lamp. What we can offer, and this is our proposal, we have a lamp, or we can supply a lamp which is working at 222 nanometers with a filter. It has an irradiation area of 22 by 50 millimeters with an output of 5.4 milliwatts per square centimeter. Here's some information about the power consumption and the input voltage. And here you can see the inverter, which is exciting the gas inside the lamp. So in the end of the presentation, if you have more information, if you need more information, I can also answer questions related to that. The next topic I wanted to briefly talk about is about functionalization of surfaces, and especially on the hydrophobicity specification and how this can help. Wet surfaces can provide the ideal conditions for biofilm formation, and therefore wettability properties of surfaces may play a crucial role. Hydrophobic surfaces can be named self-cleaning surfaces, and we have a very popular case, which is the Lotus leaf, which has a great potential of antibacterial properties. So this is a field that also can be under study now given the situation. But in order to get hydrophobic materials, you need to functionalization surfaces. And this means that you need to change the surface properties that depend on the geometry in micro and nanoscale and the surface chemistry. There have been many research activities based on that, and it has been demonstrated that laser can change both properties, but even though the exact mechanism is not known. But it's a reality that laser can change that. So I'm going to show you a video with from one of our partners, SPI Lasers. They are manufacturers of fiber lasers. And in this video, you can see the hydrophobic effect. The drop is sliding on a surface which is metallic, it's aluminum, and has been treated with a laser. Just a second. So you can see the one that has been treated is dark. The one that has not is not that, it's lighter. And here, in order, or the effect that has been demonstrated is that you have an hydrophobic surface, which means that you have contact angles of above 155 degrees and roughness of less than 10 microns. And the thing is that this has been made with a nanosecond laser. There have been many research studies doing this or getting this effect with picosecond and femtosecond lasers. The advantage of having it done with nanosecond lasers is that it's 5 to 10 times cheaper in price than the other technologies, which make it much more attractive for industrialization. So, as mentioned, I have been going quickly through all these two technologies. We have, I have more information to share if you want to contact me, or if you have more questions in the end of this presentation, I would be glad to answer.